Hello everyone. For this chapter, it's actually chapter 3 on AC circuits, and you can see that these are the contents of whatever that we're supposed to cover. So first of all, we're going to look at like AC circuits, the waveform, the values, and then we will move on to the circuits where later on you will have a look at pure resistive circuit, pure inductive circuit, capacitive circuit, and then a mixture or combination of all these three elements. That's when we learn the impedance concept. Alright, and then we will learn a little bit more about the difference between apparent power, real power, reactive power, and so on, because with different components then we have different sort of power or the term that we actually call it. So for some of you, this might be quite familiar to you, because I believe that some of us would have learned about this a little bit in our physics last time. Alright, but anyway, let's just first start with what we think or what do we know about AC signal. So you know AC is always related to DC as well, right? So DC basically means direct current, alright, and then AC means alternating current, alright. So this is an example of alternating current. So what's the difference between this DC and AC signal? So basically for DC signal, what happens is that it actually moves in one particular direction only, alright. But for AC, it speaks for itself. The term itself, it's alternating current. So you can see that you will have a positive cycle, and then it can also be negative at a given time, alright, instantaneous time. And usually this is just a representation or expression of what a voltage signal is for an AC signal, usually being represented with a sine wave, alright. So Vmax here is usually what we know as the amplitude, or where the highest peak of your signal is. So that's denoted by your Vmax, alright. This is basically a sine wave. Sine wave is like a slinky, alright. So omega t. This is something that we're going to look at a little bit later on. If you look at it in terms of the circuit, alright, this is an alternative source, alright. And then we have a resistor here. So alternating current just basically means that it can go from one side and go from the other side. Okay, just as simple as that. So these are just some examples of various sources of AC power, but I think if we can just sort of name some very quickly and all that, you will see it everywhere basically, because we have electricity all around us, right? Your aircon, thermal plant, AC generator over here, windmill, solar panel, function generator. These are just examples of what sources that actually use AC power, alright. So for some of you, we just go a little bit with the basics of AC voltage, yeah. So one way of generating an AC voltage, alright, we actually play with the rotating a coil of wire, alright. This would be a conductor on its own, alright, at a constant angular velocity. Just basically it means that it's on a regular speed in a way, but we call it velocity just because it involves both magnitude and direction as well, alright, in a fixed magnetic field. Okay, and then what happens is that figure 3 here actually shows this figure over here, alright. So you can see that you can have like a coil of something, and then you have a presence of two magnetic field. This, I think for some of you, you're quite familiar with it already, because this is something of the example of what you may have seen in your physics last time, alright. So the result of the voltage is usually proportional to the rate at which the flux lines are cut, alright, over here. So this basically means that the faster the flux lines are being cut, then the higher the voltage that you actually get, alright. So the resulting voltage is proportional to it. So the rate of cutting flux varies with time, definitely. So it basically means also that the voltage actually varies with time. So this basically just means that when you actually have this thingy over here being rotated again and again and again, right? So like for example, this particular position over here is where it's at 0 degree position. Alright, it basically says that the coil sides actually is moving parallel to the flux line. Alright, so the criterion for electricity or for AC voltage to be generated is as such that you have to have the flux line being cut. Now in this case it's in parallel, therefore the induced voltage will be 0, which means there's no reaction at all. Alright, but what happens when you turn it into, let's say, like 90 degree position? What happens is that you have a current direction that's out of slip of your ring A over here because your flux line is being cut. Alright, just imagine that you have this slip over here, this ring over here, and it's being rotating in a circular motion. Alright, so what happens is that when it is rotating, what happens is you can have your voltage over here, and what happens is that at first it will be 0, right? But as it is rotating and so on, you're definitely going to start to have some voltage, and then what happens is as it goes on rotating and all that, it will actually form a shape of this. And how or where it particular is for this voltage over here, it actually relies on the angle of where your slip ring is rotating towards. Alright, so it really depends on the angle of how many degree it has actually turned, and then it will have the 0, and then the maximum over here, and then 0 again, and then on the other side of the maximum side, but on the opposite side, and then to 1. Alright, so that's basically just a concept of how it works. So that's basically how it actually is, but unfortunately I don't think that this can be played. This is what I mentioned about just now. Alright, this is when it's at 0, and this is the position of your coil. Alright, just like what I've mentioned just now, and the generated voltage. Yeah, so every time voltage is generated when flux line is being cut. Alright, to what extent it's being cut and all that, it really depends on the coil position. Alright, so that's definitely one thing that you should take note on. But this is just really like for you to understand the principle of how AC waveform actually goes about. Alright, so now we move on to the waveform. There are some terms that you will definitely need to know: frequency, period, amplitude, and peak value. Yeah, so periodic waveform. Periodic waveform basically means that it's a wave and it just goes on like cycle by cycle. Alright, it means for every cycle after it completes its signal, it actually repeats itself again. Alright, so for example, if it's a sine wave, so after one cycle, then it will become like it will repeat itself into a simply S shape like that for a sine wave, and just repeats itself again and again. That's what we know it as periodic waveforms. Okay, repeat at regular intervals regardless of their wave shape. Alright, so how do we actually characterize a waveform? We usually look at it in terms of the frequency, period and frequency. Frequency is denoted by a small f. Alright, period is denoted by a capital T. Alright, its amplitude, instantaneous value, and so on. So f and t are actually interrelated. We move on to frequency first. Frequency basically means how many cycles per second that your waveform goes. Alright, so if and frequency, the unit is hertz. Alright, if it's 1 hertz means it's actually 1 cycle per second. Alright, if you look at this is how it goes by 1 cycle. You know how 1 cycle goes? It usually starts from the beginning and it should end at the same point where it actually begins. Alright, so it's from this point here. If it starts from 0, then it will end at 0. That's how we define 1 cycle. Alright, so in this 1 second is actually 1 cycle, therefore it's 1 hertz. So you can see that if it's within 1 second and you have 2 cycles, then we actually say that the frequency is of 2 hertz. Alright, same goes for this one. Then it's 60 hertz means there are 60 cycles in 1 second. Alright, unit would be hertz.